Welcome to Homework Lib.
Hello, in the question we have given that the radius of inner conductor of a long coaxial cable is A, the inner radius of outer conductor is B. So if I draw the cross section of this conductor, so it will be like this. So I am drawing a cross section. So this radius they have given it as A and this radius is given as B. So they have given one boundary condition that the inner and the outer conductor are at potential. So this is at potential V naught and this is at the potential 0. So we have to determine the electric potential and the electric field strength. So now in order to do this, we will use Laplace equation. So now only the radial component will survive over here. So del square V will be equal to 0. So this is the Laplace equation. So now we will use the cylindrical coordinates over here. So del square in cylindrical coordinate is this. So del square V is equal to 0. So if I plug in the Laplace equation, so this is the radial part which we are interested in. So we will do this 1 upon r. So we will take the radial part, so the first component over here. So and we will equate to it to 0. So if I send this r over here, I will get dabba by dabba r plus r dabba v by dabba r. So now, so this is differentiation of some constant because it is equal to 0. We know that differentiation of any constant is equal to 0. So I can say that this is a constant. So r d del v by del r will give me some constant. Let us call that constant as a. So sending it to the other side. So rearranging this equation, I will get dv is equals to a dabba r by r. So integrating on both the sides, we will get v as equals to a ln of r, because integration of 1 upon r dr is ln of r, plus b. Let us call this as equation star. Then we have given that at r is equals to b. See, at r is equal to b, so we have the potential as equal to 0. So this potential is given to be 0 and this potential is given to be v naught. So then if we plug it in this equation star, I will get 0 is equals to a ln b plus b. So rearranging the equation, I get b as equals to minus a ln of b. Now this is one equation. Now we will put the second boundary condition, that is at r is equal to a, v is equal to v naught. So v naught will be equal to, so if I plug the value over here, so I get v naught a ln of at r is equals to a we are putting. So this will be a plus b as it is. And then we will plug the value of b which we have found above. So we get a ln a minus a ln b. So using the log property, I can write this as a ln a minus b. So from here I can find out the value of a, which will be v naught divided by ln of a by b. So with this equation, so let us call this as equation 2. Let us call this as equation number 1. So plugging the values of equation 1 and 2, so equation star becomes v is equals to v naught divided by ln a minus b times ln r, and this is b. So b is a ln b, but a is this v naught ln a by b and ln b as it is. So if I see this, so again I can use the log property over here. So I will get this v is equals to v naught divided by ln a by b times ln r by b. So this is my potential. So this is one of the thing that is asked in the question. Now in the second part we have to find out the electric field. So electric field, as we are interested in the radial component because it is very long, so the z component will be 0. So the electric field will be minus grad v. So gradient is dabba by dabba r of this v. So if I differentiate this, so now this sign I am absorbing over here, so this becomes b by a, and ln of r by b will give me 1 upon r. So because this b, I will again get b, and then differentiation of r by b is 1 upon b, so this b will get cancelled and we just get this part. So the electric field will be equal to v naught divided by r ln b by a. So this is the electric field in the radial direction. I hope you find the solution useful. Thank you.